Welcome to AI Paper Slop. Today we're jumping straight into a new paper from Zhejiang University called Can Foundation Models Reach a Target Viewpoint Through Active Exploration?
Yeah, and it's a fascinating one.
It really is. So if you're an ML engineer or anyone building embodied agents, here's the core insight right up front. Off-the-shelf foundation models like GPT-4o, GPT-5, Gemini 3.1 Pro, they are surprisingly terrible at active 3D exploration.
Just remarkably bad at it.
Right. Specifically, this task called Target Viewpoint Reproduction, or TVR. Now, humans score about 93% at finding a specific 3D viewpoint. The best closed-source model gets 12%.
Barely double digits.
Exactly. And the paper identifies the bottleneck. These models, they just fail to map spatial discrepancies to body translation. They know what they're looking at, but they don't know how to physically move their bodies to fix it.
Yeah, they lack that motor mapping.
So to fix this, the authors introduce a post-training pipeline. They prove that visual action supervised fine-tuning, importantly without chain of thought, combined with live multi-turn GRPO, boosts a 9 billion parameter open-source model all the way up to a 51.4% success rate.
Which is a huge leap from the baselines.
It's massive. So for you listening, here is our mission today. We're going to explore this TVR bench, figure out exactly why multi-billion parameter models get stuck, like literally walking in circles,
right,
and break down why traditional step-by-step RL and chain of thought actually destroy closed-loop performance.
Right. And to really grasp why they fail, we kind of have to redefine spatial intelligence first.
How so?
Well, most benchmarks right now measure passive spatial intelligence. Like, you give a model a static image or maybe a video and ask, is the cup to the left of the laptop?
Right, just asking what is where.
Exactly. It's completely passive. But Target Viewpoint Reproduction tests active intelligence. You are dropped into an environment, given a target image, and you have to continuously issue motor commands until your current view perfectly matches that target.
So it's like someone handing you a Polaroid of a coffee mug taken from a really specific angle and dropping you in a hallway.
Yeah, that's a great analogy.
You can't just identify the mug. You have to physically walk into the kitchen, adjust your body, tilt your head until your eyes capture that exact same framing.
Right. And the mechanics of the TVR bench simulation make that so rigorous. They use environments from AI2, Thiek-Or, and Proctar R10K.
Okay.
And the agent has a discrete action space. Just 9 choices. Move ahead, back, left, or right in like quarter-meter increments. Rotate left or right 45 degrees, look up or down 30 degrees, and crucially, a stop action.
Oh, so it has to know when it's finished.
Exactly. The episode only counts as a success if it issues that stop command when its camera pose perfectly matches the target viewpoint. A complete 6-degree of freedom match.
Wow, so there's no partial credit. And they evaluate this across a grid, right? Single room versus multi-room, and then easy versus hard environments based on, like, visual richness.
Yeah, easy tasks have a lot of objects, like a cluttered kitchen, to use as landmarks. Hard tasks are sparse. Think of a nearly empty hallway.
Right. And you'd think a trillion parameter model could just stumble its way to success, but the baseline numbers are just a bloodbath.
Oh, it's brutal. Like you said, humans hit 93% on a subset of this benchmark. Gemini 3.1 Pro topped out at 12%, and the best open source model they tested natively, Quinn 27B, hit just 7.8%.
7.8%.
Yeah.
My first thought was maybe the models just couldn't process the visual fidelity of the simulation.
Right, that's what you'd assume.
But the first major bottleneck they found was actually memory overload. And bizarrely, the models did better when they had less visual info.
Yeah, that's such a critical detail. They tested 2 memory formats. First is action only, where it sees the current image, target image, and just a text history of past actions.
Like a log that says, move ahead, turn left.
Exactly. Then they tested visual action memory, which gives it the full multi-turn visual history, every image it saw along the way.
And the text history won out.
Across the board, open source models did better with action-only memory. The average gap was like 3.8 percentage points.
Which feels super counterintuitive until you think about how transformers actually process data.
Right, under the hood.
Because parsing a text string is computationally cheap. It's native to an LLM, gets text logic. But stacking, 30 high-res image embeddings into the context window,
it just completely overwhelms the attention mechanism.
Yeah, you get massive attention dilution. It struggles to cross-reference all those overlapping pixels to figure out where it just was.
The base models just haven't been trained to build a continuous 3D map from visual history. But the second bottleneck is the real structural failure, body translation.
Oh, right. This was fascinating.
When they dug into the logs, the models weren't failing because they couldn't rotate their heads to frame the shot. Translating 2D pixels into 3D movement is just computationally unnatural for them.
Yeah, the ablation study proved this perfectly. They restricted the task so the agent started at the exact right spot in the room. It only had to rotate and tilt its head.
Just a pan and tilt.
Right. On that task, an untrained Quinn 3.59B succeeded 80.5% of the time.
That's a huge difference.
It totally gets visual alignment.
Yeah.
But the second they kept the head pitch and yaw the same, but made it actually translate its body like walk across the room, success plummeted to 10%.
And if you look at transformer architecture, it makes sense. LLMs process sequences. To walk across a room, it has to calculate that if a cabinet gets larger in its field of view, it means it's moving forward.
Right. Depth and object permanence.
Exactly. That continuous geometric transformation, its next token prediction, just isn't built for that natively, so they just panic.
Yeah, they panic. The failure modes in the logs are so consistent they either start walking in circles, pacing back and forth because their spatial map breaks, or looking in loops where they just tilt up and down until they hit the step limit.
It's kind of sad to watch, honestly.
And when they finally hit stop, the false stop rate, the f-stop, is catastrophic. For the Quinn 9B with visual action memory, the f-stop was 100%.
Literally every time it chose to stop, it was in the wrong place.
Every single time. GPT-5 was a slight exception, right?
Yeah.
It had a lower f-stop, meaning when it stopped, it was usually right. But its overall success was still only 8%.
Yeah, because it was way too conservative. It would just time out looking in loops without ever committing.
So this is where we really have to push back on the current AI dogma, the whole more compute equals better results thing.
Right, the scaling laws.
Yeah. Normally, if a model struggles, we say, turn on chain of thought. We've seen Coty solve crazy math and coding problems. So I figured, why not ask the model to think about the 3D space, analyze the geometry, and then move?
It's the logical assumption, but the data completely rejects it.
Wait, totally rejects it.
Totally. They enabled Quinn's native thinking mode. It generated roughly 10 times the number of tokens, outputting all this extensive geometric reasoning about the room.
Okay, so it's doing the work.
It's doing the text work. But the success rate remained completely unchanged. Generating paragraphs of text about a static frame didn't teach it the physical mechanics of moving.
Wow. So scaling laws and organic reasoning both fail. So they had to build a post-training fix from scratch, starting with that Quinn 9B baseline.
Right. They generated rule-based expert trajectories in the simulator. Basically, an algorithm calculating the absolute shortest path.
Like a perfect GPS route.
Exactly. And they used that perfect data for supervised fine-tuning, or SFT.
And this SFT phase actually flips that memory bottleneck we talked about, right?
It does. The baseline got confused by past images, but the fine-tuned visual action model jumped to 50.8% overall success.
That's huge.
It dominated the single-room tasks. The capacity to process visual history is in the 9B model. It just needed SFT to unlock it for active perception.
But the crazy part of the post-training is what they call the coat penalty.
Oh, this is my favorite part of the paper.
It's so wild. They wanted to see if adding supervised chain-of-thought reasoning to the fine-tuning data would push that 50% even higher. So they used a vision model, MAMO v2.5, to annotate rationales for every expert step.
Forcing the model to explicitly note landmarks and justify its next action.
Right. And the result was a massive regression. Adding Coty annotations dropped the overall success from 50.8% down to 35.6%.
It actively made it worse.
It reminds me of trying to parallel park. If you just rely on your visual action history, look in the mirrors, turn the wheel, feel the car move on, you do fine.
Sure, it's instinctual.
But if you try to verbally narrate every geometric angle and distance out loud while parking, you overload your working memory. You get confused and you hit the curb.
That is the perfect analogy. Because active perception is continuous. It's reactive. When you force the model to output a paragraph explaining why it's moving a quarter meter,
you're interfering with the reaction.
Exactly. Mathematically, during fine-tuning, the loss function is being pulled in two directions. It's trying to minimize the error for generating good reasoning text and minimize the error for driving the physical body.
So the text becomes a distractor.
Yep. The model learns to output really plausible-sounding text, but its physical control just degrades.
Okay, so visual action SFT without chain of thought gets us to 50.8%. Great. But that's mostly single-room success.
Right. It still struggled with scale.
When you put it in a multi-room house where it has to go down a hall and into a bedroom, SFT isn't enough. So to conquer long distance, they turned to reinforcement learning, specifically GRPO.
And how you apply GRPO is the hinge point of the whole paper.
Yeah, break that down for us.
So first, they tried single-turn GRPO. This is offline RL. They took the expert trajectories, broke them down step by step, and trained the model to match the single correct action for a single image.
And when I read that this massive offline training regressed the model, it dropped from 44.2 on the action-only baseline to 26.2%. I figured the data was noisy.
A lot of people would assume that.
But it's not the data, it's compounding errors in closed-loop systems, isn't it?
Precisely. Let's look in the math. Even with perfect offline data, say your model is 72% accurate at picking the right next step. That sounds okay.
Sure, a C minus.
But an average trajectory is 30 steps long. So over 30 steps, that 28% error rate compounds. 0.72 to the 30th power is effectively zero.
Right. Executing 30 perfect steps in a row without a single mistake is practically impossible.
And that's not even the worst part. In offline training, the model only sees perfect expert states, optimal images. It never sees what a mistake looks like.
Oh, right, because the expert never makes a mistake.
Exactly. So at test time, if the model makes one slight error, like it turns left instead of right, it's suddenly in an off expert state. It's staring at a corner it never saw in training.
And it has no idea how to recover.
None. The policy completely collapses, starts walking in circles, and the false stop error just skyrockets.
So step-by-step offline imitation is a dead end here.
Completely. Which is why they switched to Multi-Turn GRPO. This is online reinforcement learning.
Live rollouts.
Live rollouts. The agent actually walks around inside the TVR Bench simulator, makes mistakes, and receives a trajectory-level reward at the end.
Let's talk about the reward function, because GRPO group relative policy optimization, the relative part is key, right?
It is. The system samples a group of trajectories for the same prompt, scores them, and normalizes those scores within the group. It updates the policy to prefer actions that push it closer to the target relative to its own baseline.
And that does that without needing a separate heavy value network.
Exactly. It's much more efficient.
And the reward structure they use is brilliant. They gave it a penalty for taking too many steps. They rewarded correct text formatting. But crucially, they used asymmetrical progress rewards.
Right, meaning it only gets points for shrinking the absolute distance to the target.
So backing up over old ground gets you nothing. It mathematically forces forward momentum. And then there's a huge terminal reward for perfect stop and a massive penalty for a false stop.
Because it's live, the model actually experiences walking down the wrong hallway. It sees the visual evidence of the mistake, sees its distance increasing, and learns to correct its path to get that reward.
It learns recovery.
Yes. In embodied AI, you can't just learn the optimal path. You have to learn how to survive falling off the optimal path.
That is such a crucial point. And this live multi-turn approach pushed the VA SFT model up to 51.4% overall.
Which looks like a small bump on paper from 50.8, but qualitatively it's massive.
Yeah, because it specifically improved the long-distance multi-room splits.
Wow.
It taught the model to explore far beyond one room, and it maintained a 0% false stop rate.
Great. The online RL completely cured the premature stopping because it learned to value the terminal reward over just quitting the episode.
Multi-turn trajectory RL forces the policy to deal with its own compounding errors in real time. It just totally validates that for physical reaction, online exploration beats offline imitation.
Hands down.
So let's synthesize the blueprint here for you listening. If you are building an active 3D perception agent, simply scaling up parameters or using off-the-shelf models won't work.
No, it's a dead end.
What you need is visual action supervised fine-tuning, explicitly without chain of thought, combined with live multi-turn trajectory GRPO. That is the current best path to closing the perception action loop.
It really is a paradigm shift. I mean, the whole industry has spent 2 years obsessed with making models think slower, deeper, more explicitly.
Right.
But physical space demands fast, continuous reaction.
Which leaves us with a really fascinating question to mull over. We talked about how making the AI think harder actually made it clumsier. In human psychology, we have System 1 for fast, instinctual physical reaction, like catching a falling glass.
Right.
And System 2 for deep, slow reasoning, like solving math. If injecting System 2 chain of thought degrades real-time navigation, do we need a completely new architectural paradigm for thinking in motion?
That's the million-dollar question.
How will next-generation agents reconcile deep, deliberate logic with the need for low-latency physical reaction in the real world? because it seems like forcing a model to verbally explain his parking job just guarantees a crash.
It really does.
Well, thank you for tuning into this deep dive on AI paper slop. Keep experimenting, keep exploring those off-expert states, and we'll catch you next time.